I would like to say thank you to all of you, but also in particular to the organizers for inviting me to come over here. I've never been to this part of India, and it's a lovely place and of great historical importance, of course, and a lovely community here that is trying to sort of, with a great predilection for science and knowledge, which I certainly appreciate. So my talk today will be of more pedagogical nature, I would say, than research nature. I would like to give you a certain sort of overview showing how interest in two different fields, in the area of secure communication, which is known as cryptology, and quantum physics, led into a very interesting fusion that is giving us lots of insight into the nature of physical world. So, of course, the title is somewhat on the provocative side. I will not talk about the real evil manipulators. I will just simply use this concept to discuss at the end of my talk the notion of free will in certain experimental scenarios and its importance for secure communication. Anyway, so the outline of the talk is somewhat like this. I will talk about a human quest for secure communication. So that will start with the perfect cipher, the notion of the perfect cipher. Then I will identify one basic component, something what we call the holy grail of cryptography. What would give us a perfect cipher? So I'll talk about the key distribution. Then I will tell you how quantum physics, in a rather unexpected way, came to rescue cryptography from a difficult situation of finding this key distribution scheme. But then it will become even more bizarre. As we go along, I'll start telling you that quantum physics rescued and brought to cryptography something very unusual, something that even today computer scientists have problems to come to terms with. It will just question the whole notion of underlying reality through questioning the existence of information. And then I will talk a little bit of where quantum cryptography is today. And at the end, I will just go for wild speculations. I will tell you what will happen if we want to communicate secretly and do not trust anyone. Literally, don't trust anyone around, don't trust devices that we use, and we even entertain a possibility that we might be manipulated by someone else, so that we don't have a free will to take certain decisions. So that's kind of overview. So let me start with a very general picture that you should have in mind when I talk. So the scenario that I have in mind here for the purpose of this talk is a very typical cryptographic scenario where you have two individuals and call them Alice and Bob, of course, not the real names, needless to say. So Alice and Bob want to communicate secretly, and there may be, however, a third person, an eavesdropper called Eve, involved and trying to intercept messages between Alice and Bob. And the question people try to solve for centuries, for long period of time, is it possible for Alice and Bob to achieve a task of secure communication? Can they communicate secretly and somehow exclude this evil eavesdropper from intercepting the messages? So they want to be sure that no one is intercepting, no one is listening to their personal communication. Is it at all possible? Well, if you analyze the history of secure communication, then you can see that people came up with all kind of very ingenious, I would say, methods of secure communication. And they were more or less associated with a written text. And as soon as humans invented alphabets, a finite system of characters, very soon they started playing with those characters and trying to conceal the meaning of certain messages. There are basically two basic things that you can do with characters of a natural alphabet. You can either permute them, or you can substitute one character for another. And in the course of history, both of them were tried with various degrees of success. For example, permutations is the oldest cryptographic system that we know that was invented using a device called skyttery. And the ancient Greeks use a device. I'll show it to you in a moment how it looks like. Substitutions, another great invention of classical era. In this case, Julius Caesar is attributed with inventing this particular cipher around 50 BC. So skyttery, this very old communication device for implementing permutation for secret communication, is actually quite simple. It was a piece of wooden baton of a certain diameter, and then a person who wants to send a message would take a strip of parchment, would wrap it around this wooden baton, and you would write a message lengthwise. So here is a message, and then what you do, you unwrap the parchment, give the parchment to a courier, a military courier in ancient Greece, and that courier would take a parchment from one military commander to another military commander at a different location. Another military commander, the receiver of the message, would have a wooden baton of exactly the same diameter. So he would take this parchment, wrap around the baton, and the message would reappear. So that device, known as a skyttery, implemented the permutation of characters for the purpose of secure communication. This is the oldest device that was used for secure communication that we are aware of. Well, Julius Caesar, as I mentioned, used another technique known as a substitution, where for each letter of the Roman alphabet, you would substitute another letter, and in his particular case, this letter was shifted by 3 characters to the left. So the substitution rule for Julius Caesar was, for letter A, substitute D, for letter B, substitute E, and so on and so forth. This ABC is, of course, appended till the end. So for letter X, use A, for letter Y, substitute B, for letter Z, substitute C. So in this case, the message that we saw before would be encrypted in this particular way. You can see for A I substituted D, for T I substituted W, for T again W, and so on and so forth. So this is another type of a cipher called substitution cipher. Now, you see, in the history of secure communication, there's a very interesting interplay of those who produce ciphers and those who break ciphers. So, what do you think? How difficult are those simple substitution or simple permutation ciphers? Well, not very difficult to break. You know, if you think about it in the right way, if you think about it in the wrong way, if you think, well, you know, substitutions, you know, it's just, there are very many possible substitutions if you have like 30-something characters. So if you want to consider all possible substitutions that you can make, that would be something like 36 or 30-something factorial of them. So that's a huge number. It's like 10 to 26 different kind of substitutions that you can make. It is a huge number. Think about it this way. 10 to the 17th in seconds is the age of the universe, right? And 10 to the 26th is the number of substitutions. So how can you possibly break a cipher if you want to try any possible substitution? You wouldn't have enough time for that. But that's a wrong way of thinking about it. There was, there was a clever invention that came in around 800 AD from the place which is today Baghdad in Iraq. And this was due to Al-Kindi, who was known at the time as the philosopher of the Arabs, who realized that in a natural language, every single character appears with a certain characteristic frequency. It turns out that the natural language is not a random collection of letters. So if you take any written language, a natural language, anything, be it Sanskrit, be it English, be it Japanese, there is a pattern to it. Obviously, there must be, because the words are meaningful. So, if you take the English alphabet, for example, a typical piece of English text, then you check the frequency of different characters, and you realize that the most frequent letter in English is the letter E. Then the second most frequent one would be T, and then followed by, I guess, S or R, and so on and so forth. So there's a well-defined statistical pattern. And also, the statistical pattern is there for pairs of letters. For example, TH appears very frequently. So if you have a piece of cryptogram that was encrypted using a substitution cipher, there is a very simple way to break it. You just, if the substitution was 1-to-1, you just look at the most frequent character, and if you assume that whoever encrypted that used English language as the base, but in fact, in almost all Indo-European languages, the patterns are very similar. So anyway, so suppose it is English, so then you say, okay, the most frequent character, my conjecture is it is letter E. And you look the second most frequent character, then you conjecture that it is letter T, and the third most frequent will be letter A, and so on and so forth. And that with few tries, you'll break the cipher. So 1-to-1 correspondence for a given letter in the alphabet to any character whatsoever today is not even considered as encryption. It's just simply changing the alphabet. The pattern of the letters just allows you to read it like an open book. So, but that idea goes back to this person, Al-Kindi. So you may say, okay, all those easy ciphers were broken. What about more complicated ciphers? Well, people invented more complicated ciphers, and in Europe, in particular during the Renaissance period, in the 15th century or so, there was a need for a secure communication. We think about Renaissance as a wonderful, at least in Europe, a wonderful revival of thinking, of arts, flourishing sciences, but it was also a very violent period of time. It was a period of time where different local rulers were fighting with each other. There was lots of cloak and dagger policy, so there was a need for secure communication. And at that time, a person who is known to most people as a famous Italian architect, Leon Battista Alberti, came up with an idea for a very interesting encryption, saying, well, okay, if 1-to-1 encryption is very easy to break, why don't we just do 1-to-many encryption? Perhaps not just one substitution, but many possible substitutions. That might be more interesting. So the idea is this. He said, well, suppose we take the first letter of a text we want to encrypt, and we encrypt it with one substitution. Take the second letter, encrypt it with another substitution. Take the third letter and use another substitution, and then repeat it. So, and he came up with a device to do it. So this is known as the Alberti disk. So you can see that you have alphabet both on the inner disk and on the outer disk. And you can position this disk in a certain way that it gives you a substitution rule. So it was like, remember Julius Caesar used shift by 3 characters, but you can shift it by any characters you want using those 2 disks. You just simply rotate them. And suppose you encrypt using a sequence of substitution using shifts 7, 14, 19, meaning the first letter shift the 2 disks by 7 characters. For the second letter, shift the 2 disks by 14 characters. For the third letter, shift by 19 characters, and then repeat 7, 14, 19, and so on and so forth. So why is it good? Well, it's good because it kind of dilutes a little bit this pattern that you see in 1-to-1 substitution. For one matter, if you have, for example, a word which has the repeated letters, for example, like cell, L will be, in one case, encrypted as E, and the same character L will appear in cryptogram not as E but as S, because a different substitution rule will be used for that. So that made things much more complicated for people to break. It's this kind of ciphers are known as polyalphabetic ciphers. And what Alberti did, he introduced two interesting things in one go. So he introduced the concept of polyalphabetic ciphers, but he also introduced this interesting mechanical device that later evolved into the most sophisticated electromechanical enciphering machine, known as a rotor. So those kind of wheels were used over and over and over in cryptography later on. So it took people some time to crack in a systematic way polyalphabetic ciphers. So you see they were proposed in roughly in the 15th century, but it was only in the 19th century with Charles Babbage, who is mostly known as the father of modern computers, managed to find a way to crack polyalphabetic ciphers in a systematic way. As I mentioned to you, as sort of technology developed, the Alberti disk slowly evolved into rotors, into concentric rotors. And probably the most famous polyalphabetic cipher that was used and then cracked was the Enigma machine that was used by the Germans during the World War II and was cracked by a Polish mathematician, Marian Rejewski. So the question then is there a perfect cipher? Is there really if you look through history, people use all kind of different devices, from Skittley to Alberti's disk to Enigma machine. All of them were cracked. So you may just rightly pose a question: is there a perfect cipher? Is there a way to communicate secretly, or will we always be exposed to eavesdroppers and there will be no secrecy at all? So the answer to this question is, there is a perfect cipher. It has been known for a while. It's known as a one-time pad, but there is a slight problem with that system. So the one-time pad in binary works roughly like this. So you write a text using binary alphabet. This thing is not secret at all. Alice then, who is the sender of the message, picks up a string of completely random characters. So they're just completely random binary characters of the same length. So that's the string is known as a cryptographic key. Then Alice would just add bit by bit plain text to the key, creating a cryptogram. So this way, a sequence of zeros and one will be created using a simple addition modulo 2, meaning like 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, but 1 plus 1 is 0. Then, because the key is truly random, the randomness of the plaintext transfers to the randomness of the key. And so there's really no pattern whatsoever. If there's, of course, in the plain text, although it is written using binary alphabet, you'll find a pattern of a natural language. But in the cryptogram, assuming that the key is truly random, you don't have this pattern because it's completely wiped out by the randomness of the key. So you have the cryptogram, you send it over to Bob, and Bob is using exactly the same method to decrypt it. So he takes the cryptogram, Bob picks up the key that is identical to that one that was held by Alice, completely random and meaningless string of characters, and by a simple addition of the cryptogram to the key, he recovers the plain text. Now, an eavesdropper who knows the method of encryption and who can just intercept the cryptogram will have no way to crack it, because no statistical analysis will reveal anything useful about this message, because it's masked by the key. So Claude Shannon, the founding father of information theory, actually managed to prove mathematically that this system is absolutely secure as long as the following assumptions are satisfied. As long as the key is truly random, as long as it is as long as the length of the message, and it's never reused, it's never recycled. So under this kind of assumptions, you can show that the system is absolutely secure. The problem is, there is of course a problem with this system, because otherwise it would have been used. And the problem is known as the key distribution. So there is a tacit assumption here that Alice and Bob have this random string of characters, absolutely identical. And because the key can be used only once, every single time they want to send a new message, they have to generate the key bits. So how come Alice and Bob, possibly in different locations, can get exactly the same bit values? So what they want is this. We want a process where two people at two different locations can get truly random bits which are identical. So somehow we would like Alice and Bob to have magic coins, so they can toss a coin and here comes either heads or tails. But whenever Alice has heads, Bob has heads. Whenever Alice has tails, Bob has tails. But the coins are perfectly correlated, but otherwise the outcomes are random. So each individual coin gives you head or tail with probability 50%. So that's what we want. Can we get it? Can we have such a process? Of course, such magic coins do not exist in any classical world, but there is a hope that we can find something of that kind in the quantum world. So now the possible solutions for solving the problem of perfect security are either going further into the mathematics, into the area which is known as public key cryptography. So that is a very brilliant mathematical invention. However, there's a problem with that. There's, security is based on, I'm not going to describe this here, but security is based on computational complexity. It can be broken by quantum devices. Basically, it basically relies on the fact that our progress in quantum technology is slow enough, and that's not a good assumption for any cryptographic system. Quantum cryptography is something that is a way out. There's just to use quantum phenomena for the key distribution. I'll say a few words, but then I just go to post-quantum cryptography and tell you that the quantum cryptography is like a first step to something even more interesting here. So public key cryptosystems is probably not worth discussing here. So quantum cryptography. So the idea can be traced to, there are somehow two different paths that led to quantum cryptography. One was proposed by Stephen Wiesner, that was in the 70s, who was playing with the concept of uncertainty principle. And the other one was kind of my work, that it was completely independent. I didn't know about his work. So mine was more sort of stressing the thinking in terms of entanglement and those non-local correlations. Then, of course, those two different approaches today are combined. Somehow the entanglement-based cryptography has many advantages and is regarded much more secure with respect of detecting side channels. So this is not necessarily just, to play my own trumpet. It's just indeed the fact that the entanglement-based cryptography is significantly more advanced in terms of security than the prepare and measure systems. But anyway, so there's a fusion of thinking about quantum cryptography in two different ways. And it all started as far as, and here comes an interesting part of the story, because it shows you how certain fundamental issues can be incorporated into something that you think is completely different. So it starts with a story of worry. So let me start with Albert Einstein. So here you can see Albert Einstein as he was already in Princeton. He was an old grand chap at this point. He already created, he already proposed, he already invented, or discovered the general special relativity and general relativity, and he was trying to grasp with the concept of quantum randomness, quantum phenomena at the time. So Einstein wrote, as you probably know, he wrote something what kind of sounds like a negative paper. It was together with his postdocs, Podolsky and Rosen. So it was known as Einstein, Podolsky and Rosen paper, where he basically says quantum physics, as it is proposed, makes very little sense. Basically, he was unhappy with the concept of inherent randomness, the fact that somehow things can happen for no reason whatsoever. And he was so much concerned about it that he was trying to derive all possible strange consequences of this inherent randomness. Basically, he was saying, physics is about telling you what will happen, about making predictions. And it's not really possible that something happens for no reason, because how would that be? The whole concept of Western science was based on the fact of being able to tell you what will happen given the current state of affairs. Something that happens for no reason makes very, very little sense for sort of a for someone who thinks about science seriously. So Einstein, of course, was trying to show what are the consequences of this assumption. And one of them was, he went so far that he even questioned the existence, showing, if you take randomness seriously, you will be questioning the concept of things like underlying reality. You see, like, if something, if a given value appears out of the sudden, so you may wonder, how come it? So from where it appeared? What was it before? And if there is a clear path from initial condition to the final one, then there's no randomness. But if somehow at some point something random happened, it just simply questions the existence of this particular value prior to that moment that it happened. So if I may say in a complicated way. But anyway, this paper showed that the quantum physics is leading you to some kind of paradoxes. And in fact, a statement that made me think seriously about quantum cryptography was Einstein, who was trying to define different concepts there in this paper, and one of them was the element of reality. He was saying, if without in any way disturbing a system, we can predict with certainty, so that means with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So in other words, you should be able to say what is the value of a given physical quantity without disturbing it. So then, according to Einstein, that would give this physical quantity a certain degree of reality. And if you're a cryptographer and think about it, and you think, okay, information is physical, then if you start, all what eavesdropper wants is to learn the value of a physical quantity without disturbing it. And so that means that all eavesdropper would like is to see a certain element of reality. And if you just remove this element of reality, then you might be able to detect eavesdropping in the system. So for example, you can take polarization as a good example. It's an intrinsic property of a photon, We cannot just measure polarization, we can only measure polarization with respect to some specific direction. And any measurement can give you two possible values, say plus or minus 1 in the units of h bar. And we may ask a question, following sort of a little bit the path of Einstein, do photons have predetermined values of polarization? So you know that polarization can be measured. So if it can be measured, you have two different values. So natural way of thinking is, of course, those values exist prior to the measurement, right? How could what the measurement does, it reveals pre-existing values. That's all what it does. So if you take this view and consider an experiment where there's a source that produces two pairs of photons, so we will come to a moment about the source. So we say, okay, well, those two photons have predetermined values of polarization. That's kind of obvious. But if this is the case, and this is, this didn't come from Einstein, but was noticed later on by John Bell and a few other people. If this is the case, then there are certain natural limitations on correlations between photons' polarizations that you can observe. So, for example, if Alice is going to choose to measure two different types of polarization, call them A1 and A2, and Bob is going to measure two other kinds of polarization, call them B1 and B2, then this figure of merit S can only have two different values, +2 or -2, and you can see it right away. So because any of those here, A1, A2, B1, B2, can be only equal +or -1 in the units of h bar, then one of those terms here has to be equal to 0, and the other one has to be equal +or -2, right? So if they're identical, if B1 is equal to B2, then this term is equal to 0, and this is equal to +2 or -2, and vice versa. So in other words, S is equal to +or -2. Take the average value, average it over, so the average of S has to be somewhere between -2 and 2, right? It's a very simple statement about correlations. Any sensible correlations where there is an attributed numerical value to A1, A2, B1, and B2, they have to satisfy this condition. However, it turns out that quantum mechanical predictions do not satisfy this. And you can show that quantum mechanical predictions tell you that the correlations can be stronger. There are ways of preparing those photons so that this figure of merit S will go well beyond the range -2 and 2. It can go into something like 2 square root of 2, from -2 square root of 2 to 2 square root of 2. And that was demonstrated by a number of beautiful experiments, starting with a beautiful experiment of Alain Aspect at Institut d'Optique in Orsay in 1980. Well, he was not the first one really who looked at this. I mean, like Joe Clauser was a true pioneer. But he came up with the most convincing, the most beautiful experiment, and showed that indeed the quantum predictions are there. But the shocking consequence of this is that it is not the case that you can attribute numerical values to A1, A2, B1, and B2. They don't have those values prior to the measurement. So the polarization doesn't exist prior to the measurement if you prepare those two photons in a certain way using those parametric down conversion. Now you say, what it has to do with this? Well, a simple line of argument here says if photons do not carry predetermined values of polarization, then these values didn't exist prior to the measurements. They were not available to anyone, including eavesdropper, right? And therefore, testing for the violation of the Bell inequalities is another way of testing for eavesdropping. So eavesdropper would implicitly impose this element of reality, and if you see the violation of Bell's inequalities, it gives you some confidence that there were no values prior to the measurement. And so that was, tested in the early days in the cryptographic context by people from my colleagues at the Defense Research Agency in Malvern and in Oxford. And quantum cryptography took off as commercial proposition. And today there are a number of companies doing quantum cryptography and doing key distribution. And this technology, be it, say, in Switzerland, where there's a company, ID Quantique, they employ quantum key distribution schemes in all kinds of ways. And there's even Asian and European proposals to do quantum crypto, doing the key distribution from satellites. So that is a beautiful thing going commercially. And, a few years ago I would stop my talk at this point because that would be a natural way to say beautiful fusion of two ideas. It became a commercial proposition, and that is something that we are very excited about. And I would say now I would pass it on to engineers who can take it over and produce beautiful devices. So I somehow at some point diverted my attention, as I was much more interested in fundamental questions. But more recently, quantum cryptography came bouncing back again with a few interesting and absolutely fantastic idea. So you see, until now, my story until now offers you perfect security. You mean one-time path supplemented with a quantum key distribution under certain assumptions. And those assumptions are that Alice and Bob have secure labs. They really, nothing is leaking from the labs, right? So once they read all those keys, there's no natural leak. Then another assumption is that Alice and Bob have free will, so they can choose what they measure. So that is a very crucial assumption, that for each case when they test Bell inequality, they measure A1, A2, B1, B2, but the choices are made randomly and independently from each other. That's a very important assumption. So the other assumption is that Alice and Bob can control and trust devices that they have in the lab. So those devices are coming from a trustworthy supplier. And also, Alice and Bob know the carriers or dimensionality of associated Hilbert space, so they know that the detectors are detecting one photon, not two photons, and so on and so forth. So there are some technical assumptions there. So surprisingly, there are three interesting twists. The first twist is that you can actually make quantum cryptography device independent. Because the security depends really on the nature of correlations, not how those correlations were generated, one can show that the violation of Bell inequalities alone allows you to distribute or to ensure security without testing any further. So in other words, you don't have to trust your devices. You can even purchase devices from your enemies as long as they generate data that allow you to violate Bell inequalities, then it's good enough. So now the modified assumption is that Alice and Bob have secure labs. Alice and Bob still will need to have free will to test the Bell inequalities, and they would require something, the so-called loophole-free violation of Bell inequalities. I will not go into details. But we don't require the fact that they trust the devices. So this is known as device-independent cryptography. This is actually absolutely amazing and mind-boggling, the fact that you can go and get a device from unknown supplier and you can still use it to your advantage. The second twist was that it turns out that violation of Bell's inequality is somewhat weird in a sense that quantum correlations violate Bell's inequalities up to a certain value of this S parameter 2 square root of 2. It's known as a Cyrelson bound. However, it turns out that the correlations that will not allow you signaling, the so-called non-signaling correlations, which are kind of reasonable correlations we are looking for, would in principle allow you to violate Bell's inequality all the way to S equal 4. So somehow the world of reasonable correlations that do not allow you to send instantaneous signals is roughly like this. So think about three sets. There's a polytope. I mean, you can sort of represent correlations as a point in some kind of configuration space. So there is a polytope of reasonable correlations, which we call a local realistic correlation, the correlations we observe. Then there's a convex set of quantum correlations, which is larger than this polytope. So there are correlations somewhere here which sort of are outside the polytope. So you see in this space, you can think about Bell's inequalities as hyperplanes, which sort of are parts of the faces, different faces of this polytope. So S equal 1 would be just this plane, and the Bell inequality tells you that any reasonable correlation should be for S equal less than 2, should be somewhere on this side of this hyperplane. So you can actually have quite a few Bell inequalities corresponding to different plane of this polytope. It's not a cube. I mean, this is a simplification. Those things are in 15-dimensional case for sort of 2 qubits. Anyway, so the quantum correlations are bounded by the Cyrelson bound. If you go with S to 2 square root of 2, you are somewhere here. And this sphere that represents this convex set of quantum correlation is all what we observe today. However, it turns out that non-signaling correlation, at least mathematically speaking, can go a little bit further. You can have a polytope of non-signaling correlations, which gives you S equal 4. We haven't observed, there's not a single experiment that ever observed any correlation there. It might be a new physics. Maybe one day we will observe. But what is interesting is that the statement about the security related to the violation of Bell's inequality says, even if we observe correlations here, we can distill secure information from that key. So in other words, we say that as long as we outside this local realistic polytope with our correlations anywhere, we will be able to have secure communication and secure key distribution. So this is actually a mind-boggling statement, because somehow we are making statements about security with respect to even yet unknown and undiscovered laws of physics. We say as long as those correlations go outside this polytope in the middle, then everything will be fine. So we are kind of like this medieval traveler poking our head outside the known world and being able to make statement about security. And there's a third twist, the last but not least, and that is related to another assumption, namely that Alice and Bob choose the values A1, A2, B1, and B2 randomly and independently from each other. You see, you can question even this assumption. And the reason you can... So you may say, well, are we not going now into a sort of more philosophical discussion about the free will? Yes, you can look at it this way if you want, but I think there's also much more pragmatic here. So you don't have, if you don't want to talk about free will, you can think about it this way. The decision whether to measure A1, A2, B1, B2 are made by random number generators in the lab. So you buy equipment, but you also have a random number generator, and this random number generator will choose which observable to measure. So now we already said that the devices can come up from any supplier, even unreliable supplier. So we are talking about device-independent key distribution scheme. But then, if your random number generators are also pre-programmed by some supplier that you don't trust, by your enemy, then you are screwed up. You are really screwed up in this particular case, because the random number generators will know what you measure, and then they can simulate the violation of Bell inequalities to any degree, and at the same time possess the knowledge. So you have to be careful in this particular case. And the question is, even if your random number generators, or if you don't have free will, or you're controlled by a manipulator who knows exactly what will you choose for a given measurement, if that control is not perfect, so for example, for every single, each time Alice and Bob will be choosing from 4 different settings, and suppose a malicious manipulator knows with some probability which setting will be chosen, not with probability 1, so it doesn't have a perfect control. So this is characterized by probability P. Of course, which setting will be chosen will vary from case to case, but we assume that the maximum probability will be P. And then the question is, suppose you know that this value P, is there anything you can do about it? And the answer, surprisingly, is yes. If this P is not too high. So in other words, for example, if you observe if Alice and Bob observe the violations of the Bell inequalities at a certain level, say somewhere here, and they know the value of P, so they know they can calculate, and that's maybe relatively new research by a few colleagues of mine and myself. They can calculate what is the maximum violation of Bell inequalities for a given P. So this is represented by this kind of green line here. And if you're above this, if you see the violation above this, then you can see, you can take this sort of, suppose if your point is somewhere here, then whenever you are above this green line, there is a protocol which allows you to distill a little bit of a genuine randomness in the key. So this is a kind of a triangle of hope, even if you are manipulated, but you have to know to what degree you are manipulated. So that is important here. So someone has to tell you that your random number generators are tweaked and give you a figure of merit to what degree they are tweaked. And then you can do something about it. If not, you either have to come up with a clever test, to what degree they are manipulated, but that kind of test is difficult to come up with, and sometimes in some cases impossible. So I think here's the scenario that someone whom you trust tells you that this device, this random number generator is tweaked, or that you are manipulated with some probability bounded by p. So that more or less concludes a talk, because what I was telling you is that, the perfect cipher, may kind of exist under certain assumptions. We are pushing the borders, we are removing assumptions one by one. And at the end, we arrived, with the help of quantum physics and some really foundational issues in quantum physics, into the limit where we say, even if you don't trust your friends, even if you don't trust your devices, and even if you are manipulated to some extent, you can still distill some secret. And so that's probably as far as we can go, because I can hardly imagine, pushing this border any further. But it's amazing that under such, giving away all possible powers that you can have, and assuming that you are even manipulated, you can still have this hope for secure communication, which of course is a positive thing. So I would like to end this talk with a question and a puzzle. You see, I'm very often asked, why is it the case that somehow physicists found a solution to the key distribution problems, and mathematicians and physicists and mathematicians and cryptologists for such a long period of time found it difficult to come up with anything? Well, I think the crucial difference is that the physicists could see that information is physical. Information is not a piece of mathematics, it's not an abstract concept. There's no information without physical representation of this information. So this physical representation of the information always exists. And what you can do with information, or what you cannot do, depends on the laws of physics rather than anything else. So this is beautifully illustrated by this puzzle that I like to give to my students, especially when they come to work. And this is actually a good puzzle to differentiate between those who are good to do experimental physics and those who are good to do theoretical physics. So let me put it this way. If you are a mathematician or logician or a theoretical physicist, you find this puzzle difficult. However, if you're an experimental physicist or an engineer, you find it easy to solve. So the puzzle goes like this. So there is this person, and there are two doors leading to two rooms. And in one room on the right, you have 3 electric switches, and in the room on the left, there are 3 light bulbs. And you know that there's one-to-one connection between the switches and the light bulbs. The switches are all initially in position off. Now, you can go to any of the 2 rooms. In fact, you can enter one and the other, and you can do whatever you want in the room. However, once you leave the room, you're not allowed to go back to the same room. So you can visit the 2 rooms. You can do whatever you want. But once you leave the room, you are not allowed to go back to the same room. Okay? So now the question is, can you figure out this one-to-one correspondence between the 3 switches and 3 light bulbs? Now I'll give you the answer to this. If you think first, if you have sort of mathematical way of thinking, you say, well, it's impossible. It's clearly impossible because, if I switch one of those switches to position on, so obviously it makes only sense to go first to the room with the switches, right? Because there you can do something meaningful. So you go to that room, and if you put the first switch in position on, leave the room, go to the other one, and you see there's one light bulb that is on, but there's ambiguity about the other 2. So that's not good. But suppose then you put 2 switches in position on. Then you go to the other room, and you see two light bulbs which are on, so there's ambiguity about those two. So clearly, by this way or another, you can just prove mathematically that it's impossible. But then comes an experimental physicist or an engineer and says, yeah, well, it's easy. What you do is you go to this room with the switches first, right? And you put one switch in position on. Go to the second switch, put it into the position on, and switch it off. So, you left the first in position on, you played with the second one, switch it on and switch it off, and then you didn't do anything to the third one. You go to the second room, and you see that one light bulb is on, the other one is still warm, because of the heat dissipation, right? So it was still there. And the third one is, of course, off and cold. So here you use physics. You use physics to your advantage. You realize that the abstract situation of light bulbs and switches is just an abstract thing, and you shouldn't think about it in an abstract way. It's for real. Those things are happening. So there is another physical process, like a heat dissipation, which can help you in this case. So the same with information processing. You see, it's for real. It's done by real devices. So we can take advantage of every single underlying piece of physics that is there. And for quantum computing and for quantum cryptography, this underlying piece of physics, which was somehow neglected when people came up with the very mathematical models of computation, was quantum physics, quantum phenomena. And this basically is like in this case. In this case, heat dissipation helps you to solve the problem. And in quantum computing, quantum communication, it is quantum phenomena like quantum correlations, quantum entanglement, that help you to solve the problem, simply because it's for real. It shows you that however powerful is abstraction, mathematical abstraction is one of the most powerful tools we use. But sometimes it goes against you. In this particular case, you have to use the power of mathematical abstractions with care. You have to really understand what kind of other things you should still leave in the picture. You're not allowed to neglect them. In this particular case, this quantum physics is essential, and it helps you to solve many problems in the area of quantum cryptography, quantum computing, quantum communication, quantum simulation, you name it.